Hey guys, 3.3 zeros of polynomial functions. Okay, so to get the idea behind this, let's consider this function, f of x equals x squared plus x minus 2. Now, equivalently, of course, I can write it in its fully factored form. Okay, now what I have here, x minus 1 times x plus 2, these are linear factors of f of x. That's the first main thing we want to be familiar with. These are linear factors. Okay? And a lot of times we're interested in getting a function as a multiple of linear factors. Generally, from the linear factors, we can easily find the zeros. So for zeros, this is whatever makes f of x equal to 0. So the zeros are 1 and negative 2. Why are 1 and negative 2 the zeros? Well, f of 1 is equal to 0, which is easy to see with this linear factor, and f of negative 2 is equal to 0, which is easy to see with this linear factor. So the main thing I want you to notice here is there's definitely a connection between the linear factors and the zeros, okay? The linear factors and the zeros. So my point is if you know the linear factor, you know the zero. If you know the zero, you know the linear factor. So that's the thing I want you to keep in mind in this section. So this gives us the factor theorem. For any polynomial function f of x, x minus k is a factor of the polynomial if and only if, this means it goes both ways, they both imply each other, f of k is equal to 0. That's the fancy math way of saying what I'm about to say. These two things are equivalent. If I know k is a 0 of f of x, then I know x minus k is a linear factor of f of x. If I instead know x minus k is a linear factor of f of x, then I know k is a 0 of f of x. It's interchangeable. So for example, give a function, okay, so this is just an example I came up with just now. Give a function with zeros, let's say 2, 0, and negative 1, that's easy for me to find. I know then that, well, here's a function that satisfies that. It would be f of x equals x times x minus 2 times x plus 1. Can you see how I found those? Right here, this corresponds to this one corresponds to this 0, and this one corresponds to this 0. So if I have the zeros, I can find the linear factors. If I'm given this in the first case, I can write down the zeros. Okay. So with that idea, let's move on. Okay. So example 1, determine if x minus 1 is a factor of the polynomial. Okay, so here's the thing we have to realize. Okay. If x minus 1 is a factor, then I know that also means 1 is a 0, right? So I don't know how to tell if x minus 1 is a factor unless I can factor this, which I don't really know a nice way to factor that right now. However, I do know how to check if 1 is a 0. One option is, of course, I can plug in 1 and see if it equals 0. But another option that's going to be very useful for us is going to be able to use that remainder theorem. Okay, now the remainder theorem was from 3.2. I believe I mentioned it in the last section, but just in case I didn't, let's take a quick look at it. Okay. This one right here, okay? The remainder theorem from 3.2 says, if the polynomial f of x is divided by x minus k, then the remainder is equal to f of k, okay? So if I were to do the division, okay, of x minus 1, if I were to divide that into some function, okay, and I can use my synthetic division, and if the remainder is 0, that tells me that the remainder is equal to f of whatever this is, f of k. So f of 1 would be equal to 0. Okay. So that would mean that that would be a 0, hence I know this is a linear factor. That's what our remainder theorem tells us. Okay. So what I can do in this case is I can go ahead and I can do x minus 1 into x cubed minus 5x squared plus 3x plus 1. Now, of course, a quicker way to do this is to go ahead and do our synthetic division. So I take the 0 here, okay, and I'm going to take my coefficients here, just like we did in 3.2. Okay, so 1, 1, negative 4, negative 4, negative 1, negative 1, 0. So question is, what did this 0 tell me? This 0 right here tells me that, well, it tells me a few different things. It tells me that 1 is a 0. Okay, if the remainder is 0, then the 0 we used here, it is a 0. It tells me that 1 is a 0, hence x minus 1 is a factor. So we just figured that out, right? That x minus 1 is a factor. So why did I bother doing this instead of just plugging it in? Well, here's the thing. If I'm taking this polynomial function, I can write it like this now. I can say x cubed minus 5x squared plus 3x plus 1 is equal to, well, I know x minus 1 is a factor. But then the question becomes, well, what is the rest of this stuff, right? How do we figure that out? Well, remember, this is the leftovers. So this gives me x squared minus 4x minus 1, if you look at this right here, okay? So that's why in a lot of cases, we want to keep this here, okay? Because then we get the leftover parts, right? Because we know if we divide this by x minus 1, that's what we had left over right here. So that's a good habit to get into, especially with some of the problems that we're going to be doing here from now on. Okay. So let's move to here. Let's move to example 2. Okay. So example 2 says, factor f of x into linear factors given that k is a 0. And I should probably give you a k value. Let's use k equal to 1. Okay. Now, so I know that 1 is a 0, which implies x minus 1 is a factor. Okay. So from this, I know that x minus 1 is a factor. So what I'm going to do is I'm going to divide in x minus 1 into f of x. Okay. And then I'm going to get the leftovers right here. Okay. So I'll do my synthetic division. I'll take that 0. I'll divide it into negative 3, negative 5, and 6. So it looks like I got 2, and then 2, negative 1, negative 1, negative 6, negative 6, 0. That's good. I expected to get 0 as my remainder, right? That confirms, yes, x minus 1 is a factor, k equal to 1 is a 0. So now I can write f of x in this form. F of x is equal to x minus 1. We can have that factored out. But then the question is, if we factor that out, what are we left with? Well, here's the leftovers right here. 2x squared minus x minus 6. Now, it does say we want to factor it fully into linear factors, but from here, I think we can use our good old-fashioned regular factoring. So 2x and x, to me, it looks like a minus 2 and a plus 3 should work out for us, right? Negative 4x plus 3x is negative x. There's our negative 6. So this is fully factored as linear factors. And you could also find the associated zeros. It looks like I have 1, I have 2. In case you don't remember how to find this one, just set it equal to 0. Okay, so 2x equals negative 3, x equals negative 3/2. So that would be the third 0 we would get from this.